We have two speakers in the next section. The first speaker is Sven Kerstan. Sven Kerstan is the head of research of Just Quantum. He has a very inspiring CV, I have to say. He studied math at the University of Cambridge. He holds a PhD in theoretical physics from King's College London, and he did a postdoc at the Center for Theoretical Physics in Groningen. He has spent more than 10 years in trading and risk management until he joined Just Quantum in 2019, where he is the head of research. Our second speaker today is Rory McLaren. He is a technology strategist in the CTO office of Deutsche Börse Group, and he holds a degree in computer science from the University of Glasgow. Welcome to both of you. Welcome Sven, welcome Rory. Your talk is titled A Quantum Algorithm for the Sensitivity Analysis of Business Risks. Welcome to Quantum Summit, welcome to stage Bob. We're looking forward to your talk. The stage is yours.
Thank you very much, and good afternoon, everyone, and welcome to our session. I hope you're finding the presentations so far as interesting as I am. As per the introduction, I am Rory McLaren, and I lead the Quantum Initiative at Deutsche Börse Group. And today I'll be presenting with Dr. Sven Kerstan from Just Quantum, the company that we partnered with to develop our first use case on the sensitivity analysis of business risk. I'd like to take a few moments at the start just to talk about the business context that prompted us to explore this area before Sven then continues and talks in detail about the approach to applying quantum methods to it and the results that we achieved. As always, there'll be an opportunity to ask questions at the end of our talk, and we'll both be available on the Meet the Speaker session if you'd like to engage further. So Deutsche Börse Group covers many different activities in financial markets, and as a result, they can be impacted by many different types of external events. In order to manage the financial risks associated with these events, we perform business risk modeling, where we create models that show the potential impact in terms of financial losses based on the estimated probability of certain macroeconomic events occurring. These events may have independent probability of occurring, as well as interlinked probabilities. The models can then be analysed using a Monte Carlo style simulation to give a probability distribution for the losses. And this is the current approach that we use, and with classical computing hardware, this can be performed in a totally acceptable time frame for our business use. The challenge arises when we perform sensitivity analysis on the model. And that's to say, when we try to determine whether small changes in the estimated probability of events occurring can have significantly overall impact on the outcome of the model. Based on the size of our current risk model, if we were to test the sensitivity by varying each single parameter independently, it would take days of computation time. Testing the sensitivity based on varying all pairs of parameters would take years, and all triplets would take centuries of computation time. And it's this complexity that led us to investigate whether a quantum algorithm could be applied to the problem. And at this stage, I'd like to hand over to Sven, who'll present the details on the use case. Sven, over to you.
Thank you, Rory. So, as Rory just said, I'm Sven from Just Quantum. Just Quantum is a small quantum software company. And well, what we generally do right now is we look at interesting use cases, and the one with Deutsche Börse certainly is one, we think. And in the process of it, we develop new quantum algorithms sometimes. And the interesting thing here is that it's quantum software for a real-world problem, as Rory just explained. So let's look at the problem in some more detail. As Rory said, Deutsche Börse has risks in various places in the world, in various business lines, and they can threaten revenues. And I give you a tiny example here. For example, in some country X, there might be a certain risk that a political crisis occurs. There might also be a certain risk that the exchange rate volatility increases. And there might be a risk that the country is downgraded by the rating agencies. All three factors might impact the revenues. For example, the volatility increase might mean that it's getting much more expensive to hedge the exposure because the foreign currency in country X might have to be converted back to euros. So each of these things has a number associated with it here. 20% risk of a political crisis, 5% risk of a volatility increase, 10% risk of a ratings downgrade. But as Rory already mentioned, in general, such risks will be connected. So a political crisis, for example, may well trigger a volatility increase in the exchange rates. It can happen on its own. The volatility can just, the markets sometimes do that for no apparent reason. The volatility shoots up. But if there is a political crisis, there's a clear trigger. And in that case, it gets much more likely that we see such a risk. And here, for example, we say it's 40% that a political crisis, if it occurs, does lead to an FX volatility increase. Now, that's a tiny section of the overall business model, which basically covers all conceivable risks all over the world. So you have this huge interconnected graph of things that can trigger each other or be triggered in their own right. And the risks cover competition, regulation, the markets, elections, and even the pandemic. All these things and some others as well will be in there. Now, how do you actually work with this thing? So to evaluate the risk, as I said, first of all, you have to, of course, list all these risks. So you list all the risks and all the dependencies, which risk can trigger which other risk. And then you have to estimate the probabilities for each of the, well, we call them intrinsic probabilities, and for the transition probabilities, so that one risk triggers another risk. Now, once you're done with that, you run a Monte Carlo simulation to simulate what could happen given this set of probabilities. You have to do this many times. Why? Well, because there are many, many outcomes, and some of them are quite unlikely, and you want to get a good idea of what can happen. So in the first run, maybe the first here, the root node is triggered, and the transition triggers the second one and the third one, but nothing else. That would be one outcome. Second run, you trigger the root node again, but this time you trigger, the bottom black node here. Third run, something else again. You do this a million times, and you can plot a histogram of the results. How many risks have been triggered? Or if you want to make it one step more fancy, each risk can be assigned a financial loss. And they can be different for each risk, but let's forget about that for the moment. So on the y-axis here is the probability of this outcome happening. And outcome here means the financial impact for Deutsche Börse. And you see there will be some shape like this. So there's a relatively high risk that there's a low impact, but there will be a tail in this distribution, which means there is a non-zero risk for a high financial impact. And that's, of course, what the risk manager is interested in, because if he sees that the risk in the tails is too high, he will have to take action. Some risk mitigation has to take place, and that's how the model is used. Now, again, as Rory already indicated, all these probabilities are estimated numbers, because for one-off events, you cannot really base this on anything else. And even if you can get some sort of statistics, they will not be very good. So you can never be quite sure if the number you put in is exactly right. Even after the fact, you can never verify, of course. So, if I say item 1 had a probability of 10% occurring, it could just as well have been 11, right? Or maybe 14, who knows? And, this goes for every single number that is put into this model. Of course, you can, do some checks for how bad are things in the obvious places, but to thoroughly check the impact of each of these little changes that you could make, and that still would more or less fit your opinion about what could happen, is a computational issue. And why? Well, if you run the simulation once, even on a big computer, you don't click and get the result, you'll have an extended coffee break before even your big computer gives you back your answer. Now, typically, this model has hundreds of inputs, which means if you change the first parameter, see what happens. You get a new histogram. Change the second parameter, you get a new histogram. A third parameter, get a new histogram. Maybe they're all fine so far. The tails look more or less the same. Everything's good. But to really be sure that none of them change the tails too much, you have to go through the entire list of hundreds of parameters. This means that you'll have hundreds of coffee breaks in a row before you get your answer. And again, as Rory already mentioned, maybe the impact of changing pairs, two parameters at the same time, may have a much bigger impact than changing one, because you might make certain avalanches in this model much more likely. So you might want to check all pairs of parameters as well. And changing the pairs of 1,000 parameters means you have to do 500,000 runs of your Monte Carlo simulation, and then you really have a problem. So as I said, then what you're probably interested in is your original result and the biggest impact that you managed to find when you modified your parameters. And then you might see that, well, whatever way around you look at it, the financial impact at your 99.5 percentile or whatever you're interested in shifts a lot. Or if you look at it the other way around, the financial loss that you're willing to take becomes maybe 2 times as likely or something like that. So to know how stable the result is under changes of your inputs, you would have to go through all the possibilities with your simulation, and that will take a long time. So let me show you the results in graphic form. On the x-axis here, you see the number of input parameters. As I said, it's typically hundreds. That can change every time you run the simulation, but hundreds is a good guess. So it can be up to about maybe 1,000, maybe a bit less. And if you look at the pairs of parameters and how long it would take on a classical machine, you'll get to roughly 10 years, a bit more of 1,000 parameters. Obviously, you can't wait that long. The quantum solution that we wrote, so we implemented this sensitivity analysis as a quantum program. Well, it also increases in the number of inputs, but you don't really notice it. It increases so little that you don't really see the increase at all on this scale here. The quantum solution in this example would be extrapolated to take 23 minutes. Why do I say extrapolated? Well, the quantum hardware for gate-based quantum computers that can actually run our model in the size run in practice is not available yet. This is a few years away. So we had to make some assumptions about what that hardware looks like and how it performs. That plus the details of the implementation can, of course, easily mean that our estimates are off by a factor of 10 or 20 even. But we got a speed increase of a factor of 200,000 here. So it's fairly obvious that this will help you a lot when you switch to quantum. Let me finally tell you what we think is pretty cool about this particular project. So first of all, this is a bit more for the experts now. When you take this risk model and implement it as a quantum circuit, it's incredibly efficient. Each risk can be represented by just one qubit, and each transition by a singly controlled gate. So it was a bit of a surprise to us when we saw how nicely this problem goes through in a quantum circuit implementation. What may be even nicer is the structure that the quantum solution has. So we implemented the risk model, used a Deutsche Börse as a quantum circuit, but then we ran a quantum amplitude estimation on it. Well, not a surprise for those who know what that means. It's essentially a way of doing Monte Carlo simulations on a quantum computer. But then we search with a Grover algorithm over the results of the quantum amplitude estimation. And what does that mean? Well, it means we run a Grover algorithm with oracles which are actually imperfect. So usually people look at oracles as telling you with certainty if something is true or not. It gives you back a 1 or a 0. But that decision, is this one of our solutions or not, is here taken by a quantum amplitude estimation, which, well, doesn't work with certainty. It gives you back a certain probability or probability amplitude that the thing is one of the ones you look for. And the really nice thing is it does work. So you might be a bit skeptical when you first think about it, but let me assure you, it does work. And the third thing which is quite nice about this is you can take the same idea and apply it to related fields. Credit risk, operational risk seem obvious, interesting areas where you can essentially use the same technique. So for those of you who are interested in the details are in a paper on the archive. Here's the URL, and it's called a quantum algorithm for the sensitivity analysis of business risks. And with that, I would like to thank you for your interest. And if there are any questions for Rory or myself, we're happy to answer them.
Thank you so much for this very inspiring talk, very interesting and quite convincing, I have to say. I think what would be interesting to me is the idea eventually to do this, like to acquire the first working quantum computers with enough power or enough qubits to do this yourself? Or is it like as soon as you get the opportunity to do this remotely, even on, let's say, one of the big companies which are currently building quantum computers to implement those calculations, to implement those algorithms and setups that you have just shown us?
For Rory, I suppose.
Yeah. I suppose referring back to Mark Scott's presentation earlier, it's not clear yet whether we'll all have a quantum chip in our cell phones in our pocket, or whether these will be cloud-based resources that we can gain access to. At the moment, we used cloud capabilities to simulate this and perform this at a small scale. And so that seems like the logical first step as quantum hardware develops further. But clearly in the future, we may find that we all have a quantum resource that we have access to. So I guess we rule nothing out at this stage.
Thank you. That makes sense, I guess. So is the idea currently, maybe to both of you, the question, like, I mean, from different perspectives, obviously, to prepare everything for as soon as you can use it on a larger scale, to actually apply it in the markets. So from the Deutsche Börse point of view, like, use it for your purposes and maybe to use quantum to as soon as it becomes really possible to apply this the way it's supposed to work, and also sell this to other companies then.
Yeah, I can go first. I think the idea is indeed to get ready now, because once the machines are there, it will be too late to start thinking about it. So we want to have as much ready by then in terms of the algorithms, in terms of the, all the technology that you need to run these things in the best possible way on the hardware.
Yeah, and from a Deutsche Börse perspective, we're conducting these quantum sort of lighthouse projects because we want to be able to be in the right place, be in the sort of Goldilocks zone for quantum computing, not too early, but definitely not too late. So this is a practical example where we can investigate and understand how fast we need to move to just be in that right spot. So that was the real purpose, I think, behind exploring this use case.
Thank you very much also for your answers. I think this is a very nice conclusion here to get ready early, because this is also supposed to be one of the messages that we want to send with our conference, with our Quantum Summit, to the industry, which is one of our main target groups here, of course, to get ready to engage with these new technologies, to be interested in it and explore the possibilities as early as possible, because as you have just said, Sven, when the technology will be available, when those quantum computers will be available, it's probably to start to investigate this, to start working on it. You should already be ready. So thank you very much for this inspiration also.